So today I'm going to talk to you a little bit about nanometer and atomic scale material control in the STEM. My name is Andre Dick from Oak Ridge National Lab. So the impetus for this research is summed up quite nicely by this quote from Richard Feynman in 1959. I am not afraid to consider the final question as to whether, ultimately, in the great future, we can arrange the atoms the way we want, the very atoms, all the way down. What would happen if we could arrange the atoms one by one the way we want them? So our system is graphene that we're looking at today with silicon dopants. And the first thing I want to address is how do we get the atoms into the lattice, the silicon dopants. Once we get them into the lattice, I'm going to show you how we are able to actually move them through the lattice using the electron beam. Once we can move them through the lattice, we can begin to create silicon dimers, trimers, and tetramers. And that's a recent result we have. And then I'm going to change gears, and if we're going to use this material for making things, we probably need to be able to get the graphene clean. And I'm going to show you how we do that. And then how we can use the electron beam to deposit carbon where we want it and turn it into graphitic structures, as well as how to heal holes in graphene, and then a little bit about future directions. So in the recent past there have been several very interesting studies of silicon dopants in graphene, and it kind of sparks your curiosity as to how these things get there. And it turns out that they got there by luck, and there's something to be said for luck. We'd just like to do it a little bit better, a little bit more reproducible. So in these cases, they put the graphene in the microscope and looked around and found the defects, which is very interesting, but we want to be able to put them there in the first place in a controllable way. So how do we do that? The result was recently published in Applied Physics Letters. So we can, if we're working at 100 kV in the electron microscope, we can position the beam on the graphene and it will drill a little hole. On the bottom we have these images are just cropped and cleaned from the same image here. These are high angle annular dark field, or HADF images. And you can see here we've created a small hole in the graphene with the beam, just letting it dwell there. And then we define a subscan box over this contaminant material, which I'm calling source material. And the beam acts to sputter away carbon and some of the silicon atoms that are in the source material. And the silicon, we believe, comes from the glassware used in handling of the material. So it's not, we didn't put the silicon there intentionally, but we quite often find it to be there. Anyway, the sputtering of this material causes it to kind of scatter off in all directions, and some of them attach themselves to that little hole in the graphene, and you can see here we've got a single silicon atom stuck in the graphene lattice. Well, science has to be reproducible, so we need to be able to do this more than once. And so here's the second example. We drill a small hole, and if we zoom in and get a nice cleaned image, we can see the hole more clearly there. And in this case, I just zoomed out and scanned the beam over all this whole area, which is then scattering lots of atoms around, knocking things around. And if you have really sharp eyes, you might be able to see that one silicon atom has already attached to the inside of the hole. And waiting a little bit longer, we get two silicon atoms that have actually been incorporated into the lattice here. So the previous, on the last slide, you get one defect for your efforts. And since I'm the one creating the defects, I decided I need a faster way to put them in the lattice. So I came up with a different technique, and that is we just define a subscan box over some region like this, and the subscan box can be moved with your mouse across both the pristine lattice and the source material. And with a 100 kV beam, you have a much higher probability of knocking out a few carbon atoms from the graphene lattice, as well as scattering the source material across the lattice. And so while you're doing the subscan, you actually get an image, so you can see in real time what's happening under the beam. And then you get something that looks like this, where we can see we have a few silicon atoms stuck in the graphene lattice. And if we do this over a larger area, we can see that we have lots of little defects stuck in here. And we can then examine these later at 60 kV if we like, to see if we can move them and play with them, study them more closely. And zooming out even further, we can see these are the areas that I've scanned heavily for some amount of time. And then the rest of the material looks like this, kind of a spider web of contamination over the whole material. Okay, so now that we've got defects into the lattice, we want to be able to move them in a controllable way. So what we do is we place the beam next to the silicon atom on the carbon lattice sites, and at 60 kV. Now we decreased the accelerating voltage to 60 kV so that we don't continue to damage the lattice. And we can actually cause the silicon to switch places with a carbon atom, and it moves over like that. And during the subscan process, this is placing another subscan box on the lattice, we can actually observe this occur and then take another image and monitor what's going on as we're making changes to the sample. So this is a little looped video of the silicon atom jumping to the next lattice site. So then we can begin to try and actually move the silicon atom to a particular lattice site that we want. So this was our first attempt at that. So here's the initial position of the silicon atom, and I arbitrarily decided I wanted to get it to this lattice site. And the little gray dot represents the initial position, and the red line represents its movement through time. Now from here to here, I began moving this before I realized that I ought to be taking images every single time it moves. So we have a bit of long motion at the beginning, and then I start taking images every time the thing moved, and eventually we do get it to the lattice site that I was targeting. And so here's perhaps a bit more convincing evidence where I took a video, compiled it all into a video. In this first video, because I was so zoomed in, I just wanted to move this around in its own ring. There's a little bit of drift, and so you'll see it drifts down to the bottom here, and then I bring it back up into the field of view, and then it gets accidentally knocked from the lattice. So here's this video. A little bit of drift, and then here I bring it up, and then it disappears. Okay, so that was 57 jumps I counted, and that's about 8 nanometers, which is, I thought, quite a long distance on this scale. Here's a second example, or I guess a third example. I just moved this silicon atom up through the lattice, up this way. Okay, so if we can move them, perhaps we can begin to build little structures. And in fact we can. So here's the first example of that, where I pulled two three-fold coordinated silicon atoms together into a dimer, and this just sort of tracks their progress through time as they're getting closer and closer together. and then they form, they're within the same hexagonal ring together. And I tried to get them all the way touching, but failed. In fact, one of them was knocked from the lattice, and it converted to a fourfold coordinated silicon in graphene. And this silicon atom takes the place of 2 carbon atoms. Well, in this case, we knocked a silicon out. So it takes, sitting at a bridge point between 2 lattice sites, if that makes sense. And then we can also perhaps make some more complicated structures. So in this example, I found this dimer sitting in the lattice, but in the next slide I will show you how we can make it. But so the top panel here represents structures that we are just observing change without intentionally bringing it on. And here we're observing a bond rotation. So below these 2 silicon atoms, and maybe it's more clear here, we have 2 carbon atoms sitting next to each other. They begin to rotate here, and actually what you're seeing is the juxtaposition of the before the rotation and after the rotation, because this rotation occurs on the order of 100 femtoseconds or so, but our beam is not fast enough to capture that. So anyway, the bond rotates. We have this new configuration. Momentarily, a silicon atom comes and sits here long enough for me to get one image of it, and then it was knocked away back to this configuration, same as C. And then it is actually recaptured, and these 2 carbon atoms that participated in the bond rotation are knocked out and replaced by a silicon. So now we have a silicon trimer, which is like a rotor that can be flipped around in the lattice. And this was fairly freely able to rotate with the beam. If you zoomed out, or if I zoomed out, I was able to agitate material kind of like previously, and I was able to reproducibly attach a 4th silicon atom, turning this into a little pyramid. We have some DFT simulations of this, but I did not include them in this video, unfortunately. And this tetramer structure was we were also able to rotate it with the beam and knock away the 4th atom and bring it back. So all of these structures at the bottom here were interchangeable, controllably interchangeable with the beam. Here's a little video of that trimer rotating in the lattice, and you can see I got it to catch a 4th atom there for a moment. Okay. So I told you I'm going to show you how we can form that initial structure. If we have 2 fourfold coordinated silicon atoms, in other words attached to 4 carbons, and we bring these guys together, they form that initial structure from the last slide. This structure can be rotated with the beam. And then I was just trying to capture a more clear image of this configuration. So I took a 10-frame stack of images, and it turns out I was actually able to capture in this 10-frame stack a little bit of atomic chemistry going on. So in the first frame, we have just this initial structure. Here it is. And then shortly thereafter, it captures 2 carbon atoms, and the lattice heals, returns back to hexagonal symmetry. This guy moves down 1 here, and then this one is knocked from the lattice, and this guy assumes fourfold coordination. So here's the video. I thought that was very cool. We're actually able to capture atomic scale chemistry as it's happening. Okay, moving on. Regarding cleaning graphene. So if we're going to make devices out of graphene, it needs to be cleaned. Graphene is notoriously filthy. So this is a clean spot of graphene, but zooming out, you can see that mostly it's covered with contamination. And this stuff is really nasty for us microscopists, and so we would really like a way to get it clean. Not just us microscopists. I mean, if you want to pattern things on graphene, most of what's there is not graphene, it's the contamination. So you have to have a way to get rid of this contamination if you want to, probably, if you want to do something useful with it. So we employed protochip's heating holder, and this is what it looks like. The sample is way down here in that little dot, and our beam is going to come in like this, and we're going to image it while we raise the temperature up. And so I raised the temperature at a rate of 1000 C per millisecond to 1200 C, and what we saw was that it just became almost miraculously cleaned instantly. Of course, this wasn't the first time I tried this. I tried several things before that, but finally we managed to find a recipe that makes it clean. And if you just heat it up to 1200 C quickly, it will become clean. And it may actually become clean at a lower temperature than that. We just found that at 1200 it does become clean. Now, an interesting thing about this is the dotted line here. This is encompassing an area that I previously imaged, and if we image an area, it doesn't get as clean. In fact, if you image it for a long time, it doesn't appear to be cleaned at all. So this was, I just snapped one image here, but you can see that just a little bit of exposure to the E-beam is enough to begin sticking down this contamination so that it doesn't come off with heat. And then here's a zoomed in view of the lattice. Okay, so after cooling that thing back down, I was not able to get atomic resolution images because we get hydrocarbon deposition, and this is probably sourced from other areas of the chip. Only a very small piece of the chip around the sample is heated, and the rest of the chip remains at room temperature. So very likely what we're seeing is migration of carbon from other areas coming into the area of interest and depositing under the E-beam. But perhaps we can use that too. So here I patterned R and L with the contamination. It's just mostly amorphous carbon, but in retrospect, I was able to get about 15 nanometer line width there without any optimization at all, just sort of playing around. Here's another example. Interestingly, if you heat this stuff back up, it becomes graphitic, which means it becomes conducting. And so immediately this suggests to me that we might be able to use this as a way to pattern nanowires on some insulating material, perhaps. It's at least worth a closer look. And then this final, I think this is the final example. This was not on a heater chip, but we've seen that, with the heater chip we can possibly control how much carbon, hydrocarbon deposition there is. In this sample, it was mostly pretty good, but in this particular area, for some reason, I was getting very, very slight amount of hydrocarbon deposition. And you can see here, this was the original formation of contamination that was there, and it's kind of grown out around it. And so I thought, well, I'm going to go look at this hole and see if a little bit of hydrocarbon deposition is enough to heal a hole. So typically, even at 60 kV, when we look at image these holes in the graphene, they tend to grow because the edges of the graphene are not as strong as the graphene lattice itself, the pristine graphene, and so the beam is actually able to knock carbon atoms from the edge, and so the holes grow. But as you will see here, got a video with just a little bit of carbon source nearby under the beam, we're actually able to heal this hole, and it disappears. So this may be a way to heal holes that are unintentional, or we found, we can repair graphene. Oh, I do have one more example. So what happens if you have dopant atoms that you don't want there? Well, if you're able to get a little bit of carbon close by, perhaps we can get rid of those interstitial or substitutional defects. And you notice the lattice heals completely. It doesn't. We're not just knocking the silicon atoms, the silicon dopants out of the lattice. It's actually healing the lattice. It's being replaced by carbon. So likely this is a chemically assisted process. Okay, so in the future, what sort of things would we like to do? So one of the troubles that we run into frequently is that the sample is going to be drifting almost invariably, and once you take an image, you don't know that the atoms are now where they were when the image was taken. So it would be handy if we had an electronic drift correction that would shift the scan area to compensate for drift, so that when you put the beam somewhere, it's hitting what you think it's hitting. So along those lines, we will need sparse sampling, because we don't want to take 10 seconds to acquire an image to determine what our drift is, because that's too long. What we need to do is we need to scan very rapidly. So here's an example. Here's a full image, and we just sampled that full image very sparsely. We actually threw away most of the data, and here's what it looks like if you zoom in and look very close. I know it's not a very bright image, but then from this data we can reconstruct an image that is not obviously not as nice as the full image, but we may be able to get the position of that defect and the orientation of the lattice, and possibly the position of the lattice from which we can infer where all of the atoms are, which is good enough for our purposes, and then we can correct the drift. This is the hope. So we have just submitted a paper on this as well, where we are trying to get the computer to understand what these defects look like and classify the structures, because in the future what we'd like to be able to do is have the computer create these structures. Like, we're not doing it by hand. We have the computer find a silicon atom, recognize that it's a silicon, what configuration it's in, pull these atoms together and build a structure out of the materials that are there. Now that's probably a long way off, but based on what I've shown you in this video, I think that it's entirely possible. So thank you for watching, and have a good day. One more thing, I forgot to mention, I'm going to leave some links in the description below where you can find the publications that are associated with much of this content. So be sure to check those out, and now have a good day.